After learning this module, you shall be able to know how to estimate a regression model in the presence of autocorrelation. You will learn about few methods. For example, you will learn about the generalized least square regression procedure for regression. You will also learn about a slight modification known as feasible generalized least square regression procedure for regression, also known as FGLS. We would also try to discuss and learn about the Cochrane-Orcutt Iterative procedure for estimating rho hat. We would also discuss about the Hidreth-Liu grid search procedure for estimating rho hat. And finally, we would learn about Newey-West method for correcting standard errors of estimates in the presence of autocorrelation. Let us understand what are the remedies for autocorrelation. If autocorrelation is present in a regression model, the estimation of the model may be carried out in the following manner, either through model specification or introducing lag dependent variable. The omitted variables case is if one suspects that the autocorrelation may be due to omitted variables, then one may test for omitted variables using Ramsey's reset test or any other appropriate test and specify the model appropriately by including suitable regressors and functional forms. Let us understand the misspecified dynamics. Sometimes the dependent variable is a function of lagged values of y and x. We can specify the following dynamic model in that case, which is that yt is equal to beta 1 yt minus 1 plus beta 2 xt plus beta 3 xt minus 1 plus epsilon t. And we can say that modulus beta 1 is less than 1. Now, according to Sargan's common factor, if beta 1 into beta 2 plus beta 3 is not equal to 0, then the true model is this dynamic model. So, we must test the hypothesis H naught beta 1 into beta 2 plus beta 3 equal to 0. If this hypothesis is rejected, then the true model is a dynamic model and we should introduce lag dependent variables in the model. We know that in the regression model, yi is equal to beta 1 plus beta 2 x2i plus so on up to beta k xki plus ui. One of the assumptions of the classical linear regression model is that conditional on x, the successive error terms are independently distributed. The above assumption implies, as you all perhaps would know, that covariance between ui and uj is equal to expected value of ui uj equal to 0 for all I not equal to j. This property of the error term is known as serial independence or absence of autocorrelation or no autocorrelation. Autocorrelation, also known as serial correlation, is said to be present in a regression model when this assumption is violated. So it implies that covariance between ui and uj is not equal to 0 for some I not equal to j. And similarly, we say expected value of ui uj is not equal to 0 for I not equal to j. In an intuitive sense, it means when no autocorrelation is present, the magnitude and sign of the error term for some observation should not influence the sign and magnitude of the error term in the adjacent observation or observations. This implicitly implies that the different observations in a data set are unrelated to each other. Presence of autocorrelation, on the other hand, implies that the various observations are correlated to each other. So, the observations in the data set may not only be treated as data points, but also as predictors for the subsequent observations. So I'm sure you understand that the presence of autocorrelation is troublesome in regression analysis because it reduces the number of independent observations in the data set, compounding the process of statistical inference. So we apply tests to find out if autocorrelation is present or not. And I'm sure you know that some of the important tests are Durbin-Watson test, Durbin's H test, Durbin's M test, Bush-Godfrey test, and Box-Pierce Q test, which I'm sure most of us are familiar with. The question now is that once we are sure that there is autocorrelation in the data series based on these tests, we have to then use alternative methods to estimate the coefficients. We would now try to learn some of these alternative methods. So what are the methods? The first and the most important one is known as GLS, or is Generalized Least Squares Regression method. In this method, if autocorrelation is present, despite correct specification of the model, then this GLS regression method should be used. GLS regression method is a very useful method of regression where the regression model is so modified that it fulfills the assumptions of the classical linear regression model, or known as CLRM, and OLS regression procedure may be used for estimating it. Therefore, the GLS procedure is applicable only when rho is known. So if the regression model is that yt is equal to beta 1 plus beta 2 xt plus ut, which we can redefine as our equation 1, such that ut is equal to rho ut minus 1 plus epsilon t, and rho is greater than minus 1 and less than 1, let's define it as equation 2. This method exploits the fact that the covariance matrix of the error term ut can be obtained in terms of the autocorrelation coefficient and variance of epsilon t. We have the generalized difference equation method, or also known as Cochrane-Orcutt method. From equation 1, we can write the following relationship, which will also hold true, and that is that yt minus 1 is equal to beta 1 plus beta 2 xt minus 1 plus ut minus 1. We can write this as our third equation, where t subscript is changed to t minus 1. We can multiply this equation 3 with rho and obtain the following relationship. That is, rho yt minus 1 is equal to rho beta 1 plus rho beta 2 xt minus 1 plus rho ut minus 1. This is equation 4. Now subtracting this equation 4 from equation 1 yields the following equation, and it is that yt minus rho yt minus 1 is equal to beta 1 minus rho beta 1 plus beta 2 xt minus rho beta 2 xt minus 1 plus ut minus rho ut minus 1. Let's define this as equation 5. This equation 5 can be written as yt star is equal to beta 1 star plus beta 2 star into xt star plus epsilon t, and define it as equation 6. In this equation 6, we can observe that yt star is equal to yt minus rho yt minus 1, beta 1 star is equal to beta 1 minus rho beta 1, beta 2 star is equal to beta 2, xt star is equal to xt minus rho xt minus 1, and epsilon t is equal to ut minus rho ut minus 1. The error term epsilon t in this equation 6 is supposed to satisfy the assumptions of the classical linear regression model. Hence, equation 6 can be estimated by the usual OLS procedure. Limitations. Let us understand the limitations of this method. The first limitation is that this method is suitable when the disturbance follows AR1 scheme. Otherwise, it compounds the errors of estimation. The second limitation is that the method can be applied only if X is not endogenous, which means the model does not include lagged dependent variables. Prais-Winsten transformation. In carrying out the above differencing, the first observation is lost. When the number of observations is large, it does not matter. But if the number of observations is less, the OLS regressors in equation 6 are not blue. That is, best linear unbiased estimators. So what do we do? What is the solution? The problem is rectified when the first observation on X and Y is transformed as y1 into under root 1 minus rho square and x1 into under root of 1 minus rho square. After introducing the first observations, the estimates of OLS regressors obtained are blue. Feasible GLS or feasible generalized least square regressions. FGLS procedure is used when the coefficient of first order autocorrelation rho is not known and the value of estimated rho, that is rho hat, is used in its place in estimating the difference equation 6. The first difference method. When one suspects perfect positive autocorrelation, then rho is equal to plus 1, in which case the difference equation 5 becomes equal to yt minus 1 equal to beta 2 into xt minus 1 plus ut minus 1, or we can rewrite it as delta yt is equal to beta 2 delta xt plus epsilon t. We denote this equation as the seventh equation, where in this equation you can observe that delta is defined as the first difference operator. Now this equation may be estimated using the OLS regression model because the disturbance term, which is epsilon t, satisfies the classical linear regression model assumptions. So this method may be used when one suspects a very high value of rho or the value of Durbin-Watson D statistics is very low. Some observations about the first difference model may be made here. First is, this is a regression without intercept. The second observation is that if rho is equal to plus 1, then the underlying series is non-stationary, but the first difference series is stationary. The third is that this method is suitable only if rho is very high or close to plus 1. To test for rho equal to plus 1, Burnett-Webb test may be used. Test statistics is defined as Z is equal to sigma epsilon t hat square, where sigma is from 2 to n, divided by sigma et square, where sigma is from 1 to n. E is the estimator of U in the original model, and epsilon hat is the estimator of epsilon in the first difference model. The hypothesis in this test is that rho is equal to plus 1, that is our H naught, and H1 is that rho is equal to 0. If the calculated value of G lies below the lower limit of D, we do not reject H naught, that is rho is equal to plus 1. Computing P using DWD statistic. Since we know rho hat is approximately equal to 1 minus D by 2, for large samples, we can use this estimated value of rho to transform data and run the regression on generalized difference equation 6. A modification was made by Theil and Nagar. They said for small samples it is not suitable to use Durbin-Watson statistics to compute rho hat. A modification has been proposed by Theil and Nagar for computing rho hat. Rho hat approximately is defined to be equal to n square into 1 minus d by 2 plus k square upon n square minus k square, where n is the sample size and d is the DW statistics and k is the number of estimated coefficients. This value of rho hat may be used for estimating the generalized difference equation. Cochrane-Orcutt iterative method of estimating rho. Iterative method entails starting with an initial value of rho hat and finding the value of rho hat through successive approximations. Steps involved in the procedure are, so the first step is estimate the regression and obtain residuals. Step 2, estimate rho hat by regressing the residuals to its lagged terms. Note in this case that this regression does not have an intercept term because the sum of the residuals is 0, making the intercept equal to 0. Now the third step is transform the original variables using the rho hat obtained from step 2 as follows. We can have yt star equal to yt minus rho hat yt minus 1. Similarly, beta 1 star is equal to beta 1 minus rho hat beta 1. Beta 2 star is equal to beta, and xt star is equal to xt minus rho hat into xt minus 1. Epsilon t is equal to ut minus rho hat ut minus 1. Step 4. Run the regression again with the transformed variables and obtain residuals. So yt star is equal to beta 1 star plus beta 2 star xt star plus epsilon t. Step 5 and so on. Continue repeating steps 2 to 4 for several rounds until the iterations converge, which means the estimates of autocorrelation coefficient rho hat from two successive iterations differ by no more than some pre-selected small value such as 0.001. Slide 19. Hidreth grid search procedure. This method entails finding the value of rho hat using a grid search procedure. The steps involved in the tests are: Step 1. Calculate different values of yt star and xt star as defined in equation 6 for different values of rho at interval of 0.1 in the range of rho greater than equal to -1 to less than equal to 1. Step 2. Run the regression yt star is equal to beta 1 star plus beta 2 star xt star plus epsilon t. Step 3. Calculate RSS, which is residual sum of the squares, for each regression and choose the value of rho for which this RSS is minimum. Step 4. Repeat the procedure for small intervals of rho around the value of rho obtained in step 3. Step 5. Choose the value of rho for which n by 2 log RSS as a function of rho minus half log 1 minus rho square is minimum. It may be pointed out though that the FGLS estimators are not unbiased, but they are asymptotically more efficient than the OLS estimators of an AR1 model. But if the regression model includes lag-dependent variables or exhibits higher order autocorrelation, then the FGLS estimates are neither unbiased nor consistent. We have another method known as Newey-West method, which corrects for the standard errors of OLS regressors. When the exact form of autocorrelation is not known, or when the independent variables in the regression model are not exogenous, then it is better to estimate the model by the usual OLS procedure, but correct the standard errors of the estimates for different forms of autocorrelation. In the absence of autocorrelation, we know OLS estimates of variance on any coefficient is variance of beta hat, which is equal to sigma u hat square upon n into variance of x. In the presence of autocorrelation, it can be shown that the Newey-West standard errors are variance of beta star is equal to variance of beta hat into nu upon sigma u, where nu is equal to sigma 1 to n a t hat square plus twice sigma h 1 to z into 1 minus h upon g plus 1 into sigma t ranging from h plus 1 to n into at hat into at minus h hat. At hat is equal to rt hat into ut hat, where t is equal to 1 to n. Z is equal to number of lakhs, and rt hat is the residuals obtained by running the auxiliary regression xt1 on xt2, xt3 till xtk with the intercept. What are the advantages of this method? The advantage is that this technique may be used even when the model includes lagged dependent regressors. But it has the limitations, and the limitations are the method can be used only for large samples. And the second limitation is that the method makes the estimator unbiased, although still it is inefficient. Let us summarize what we have learned today in this module. We have learned that autocorrelation is present in a series if the standard assumption of the classical linear regression model, that is covariance between ui and uz, which is equal to expected value of ui uz, is equal to 0, that is for all I not equal to z, is violated. Then we have to first ascertain with the help of certain tests whether it is present or not. Once it is confirmed that we have the problem of autocorrelation, then the presence of autocorrelation in the regression model can be dealt with in several ways. In case autocorrelation has arisen due to incorrect model specification, then the most appropriate method is to specify the model correctly, which is automatic from the problem. Now, this can be done by introducing the omitted variables or lag dependent variables. If autocorrelation is present despite correct specification of the model, then the generalized least squares or GLS regression method should be used. But the GLS procedure is applicable only when autocorrelation coefficient rho is known. When rho is not known, then we apply FGLS or feasible generalized least square regression method, and the estimated value of rho may be used in place of its true value in that situation. There are several ways of estimating the value of rho which we have learned, namely the Durbin-Watson method, the Cochrane-Orcutt method, and Hidreth-Loo method. When the exact form of autocorrelation is not known, or when the independent variables in the regression model are not exogenous, then it is better to estimate the model by usual ULS procedure, but correct the standard errors of the estimates for different forms of autocorrelation by using the Newey-West method of standard error correction.